Thank you for the introduction and for the opportunity to be able to speak in this seminar today. Yeah, so the title of this talk is Tate Homology and Powered Flybys, and it's based on my new paper. So if you want some more details, some more explanations, you can just type the title into the archive and you will be able to find it. Yes, so what was the main result, the main goal of this paper? It's the following theorem. So in the setting of the planar circular restricted three-body problem, there are infinitely many symmetric consecutive collision orbits for all energies below the first critical energy value. And we can say even more about this orbits. These orbits intersect the symmetry axis on the straight line between the second and the main body. Okay, now what does that mean? Okay, so first the planar circular restricted three-body problem. We start with two massive bodies. Let me try it like this. Two massive bodies. And they attract each other by Newton's gravity law, and they move around each other in a circular motion. So that's the circular part. And of course, everything is in two dimensions, so planar circular. And now in this physical setup, we have a small spacecraft, and we want to know how this small rocket moves in this given system. Yes, and so that's the setup of the restricted three-body problem. And now we found that there are infinitely many symmetric consecutive collision orbits. So these consecutive collision orbits are a very special type of orbits. So they start here in the collision point of the planet, then move something like this here, then are symmetric with respect to this axis here, and go back and hit again the collision point, so consecutive collisions. And so this is true for all energies below the first critical energy value, which just means that the spacecraft always is bound to this planet here and has not enough energy to reach this other planet. Yes, and then finally, we're also able to say something about this orientation of the symmetric consecutive collision orbits. And that is that the orientation of these orbits are in such a way that they intersect here this symmetry axis of the symmetry of these orbits. Yes, maybe some note on how we mathematically describe these consecutive collision orbits. So first for the collision point, which we are here, we define it as a Lagrangian subspace simply by putting for the normal configuration or normal phase space, we want that Q is 0 and the momentum is not important. So if we start here, we can end up here with another momentum. Yes, and of course, since in this case we have the symplectic form given like that, that's then a Lagrangian subspace. And the symmetry axis, which is of course here, that part that corresponds also to a Lagrangian. Yeah, simply by saying, okay, the symmetry axis is this part here. So, and of course we know we want the orbits to intersect, have momentum here vertically to this line, so that we can put them together and have a well-defined orbit overall. And so mathematically, a consecutive collision orbit is an orbit which starts in this Lagrangian and ends in this Lagrangian subspace. Yes, and we found that there are infinitely many of these orbits. Okay. Now, before I want to go into the mathematical details, I want to give some motivation. Why are these orbits interesting? Okay. So one important application for these consecutive collision orbits are powered flybys. So the very general idea, let's first draw it in the Kepler problem, is we have here a massive body and we have here spaceship. And then the idea is that the gravity of this big body drags us in, and then we fly very closely by this massive body. And then at this point, we boost. So that's where we use our fuel, not before, right at the point where we are the closest to this body. And this then will give us a lot of kinetic energy, way more than if we would start boosting here or here. And the idea behind this is the following. So if we have a rocket, how it usually works is we use the conservation of momentum to increase the velocity of our spaceship. So let's say we already have certain velocity given, and then we can boost, use the fuel. So we eject a very tiny portion of fuel at very, very high velocity. And this will give us then a gain in velocity, a very small one, delta V. And if we now calculate the kinetic energy we gained with this maneuver, we see the following. So kinetic energy as usually. So now we assume that the mass of the fuel we use is very small compared to the mass of the spaceship. Yes, and if we now calculate this, we see, of course, we get our kinetic energy plus the gain.
M is the mass of the spaceship?
Yes. Exactly. So this is here just some very, very tiny thing we don't really care about. This here is the old kinetic energy our spacecraft had before, and this is now the gain of kinetic energy. And what you see here now is that the gain actually depends on the starting velocity. So before we boost and use the fuel. So the faster the rocket initially is, the more kinetic energy we can gain by using our fuel. And so that's the reason why here we want to fly very close to the planet and then boost, because there the most of the potential energy was converted into kinetic energy, and so the velocity here is very, very high. So that's the idea behind the powered flyby. The gain of kinetic energy is very big if the starting velocity is very high. And very interesting, this phenomenon is called the Oberth effect, after Hermann Oberth, who already thought about such ideas in 1923, which is quite remarkable. Yes. So now how, the first I want to go. So what I want to remark now is, so it kind of seems like this violates conservation of energy. But the reasoning why it doesn't actually violate conservation of energy is the following. So as a rocket gains kinetic energy, so does the fuel which is stored inside of the rocket. And then if you burn the fuel, you don't just profit from the internal energy of the fuel itself, but also from the kinetic energy this fuel gained in the rocket. Okay, now where's the connection to consecutive collision orbits? So the picture we had is we are now in the three-body problem, not in the Kepler problem anymore. And yes. So now consecutive collision orbits look, well, to be honest, like, of course, we remember these planets move around each other in a circular motion. So what we actually have here is a rotating frame. So even though I draw here very nice looking orbits, in reality, they probably wouldn't look that nice. But yes, it's just to show a concept. We have these consecutive collision orbits. They of course have now some well-definedness issue at first, because here in the collision point, well, gravitational potential is 1 over r squared, and so it diverges here in the 0 point. So we have to regularize our Hamiltonian, and so the simple answer is we regularize it by everything that hits this collision point bounces back the way it came. And since we are in a rotating frame, this corresponds then, so usually it doesn't correspond then to orbits which bounce back and forth on this orbit, but because of this rotating part, it probably bounces back something like this. And the corresponding orbit we now have is the following. So after we regularized our system, we then have a well-defined Hamiltonian system on everywhere, and we can use that the Hamiltonian vector field is continuously dependent on its initial condition. So if we vary this initial condition slightly, we still get a somewhat similar orbit. Yes, and so that's the idea. So of course, if you have a spacecraft, you don't want to really fly these collision orbits, because then this mission failed. But you can fly a slight variation of it, so you don't crash into the planet, but you fly very closely around, and then fly back here. So then you can boost the first time to gain some kinetic energy, and then assume maybe you still don't have enough kinetic energy to reach this other planet. So what you then can do, you can loop around, fly another flyby, boost again, and then you gained a lot of kinetic energy from this maneuver. And that is where you can use this consecutive collision orbits. So we know that for every consecutive collision orbits, we can, by continuity of the initial conditions, also find such flyby orbits close by. And the also important aspect of consecutive collision orbits is that we have a rather sharp mathematical definition for them. So we can don't have to formulate something like, and then it almost misses the planet, but we can say, okay, it starts in the Lagrangian for collisions and ends in the Lagrangians for either then collisions or the symmetry condition. Okay, now let's talk about this regularization we use. So it's quite, so the usual regularization, I think, is using is Moser regularization. But here we now use Levi-Civita regularization. The idea is the following. So we first interpret our phase space as C2, which is not so strange since the phase space is just R4 in this case. And then we pull back the Hamiltonian with the following map. Yeah, so we map from C to C, and then we map here the set to a set squared, and here W to this part. And so how the regularization then works is we have our initial Hamiltonian, and then we regularize it to H, pulled back with L, and then multiplied with this absolute value of Z squared. And the interesting part of this regularization is that now our configuration space variable Q corresponds to a Z squared, and the P variable corresponds to this one here. And this then leads to a very interesting splitting of this Lagrangian, which ensures the symmetry. So let me try it again. We had our usual setup here. And then we had that the whole real axis is the symmetry. So it's like the configuration space part of this Lagrangian we want to end in. Yes. And so what is the configuration space part? It's just R. But this now corresponds to a Z squared. So when we are now in this, so that's a picture for the unregularized physical world. And if we're now in this regularized world, then this splits into two different kind of Lagrangians. So I just want to emphasize here the configuration space picture. The R can be achieved in two ways because of the Z squared here. We can either choose R squared, of course, is still in R, and this then corresponds to the positive part, and we can take an I times R, which is the negative part. So if I draw it now in this picture, so here we have the negative part, which is the configuration space part of now a different new Lagrangian we call LS, which is, of course, here defined in this regularized setting. And we have a positive part called an M. Yes, and so here this corresponds to.
I'm sorry, could you repeat maybe what are Z and W in terms of the positions of the
yes
of the planets, please?
So LS should stand for solar eclipse. So if we assume we have here the Earth and the Sun, and our small satellite would be the Moon, then the Moon would cross here, which then corresponds to a solar eclipse. And here the Moon stands for a lunar eclipse. So if the Moon would pass on this side, then of course Earth would block the sun from hitting the moon, and so we have a lunar eclipse.
No, but I mean, in general, what are Z and W? In a general position, I don't mean in the real case. I just mean in general, what are Z and W, and what's
Well, so these are the variables in the regularized setting, and well, the regularized setting is not really the physical system anymore, because we of course regularize it to make it suitable for our case. So if we want an interpretation, then we have to use this map again, and then you get back your configuration space variable by squaring, and your position by performing this operation. And then you can again interpret what you found.
Maybe one way to think about it, Claude, is like you taking the double cover of you go to a double cover. You can think of it like if you're in low energy near the planet, then you have a bounded sort of level set.
So it's a branch double cover in the Q variable.
Yes, over the Q and the piece, so both of them.
That's not, I don't know, maybe it's not, okay. Just go ahead.
Okay. Yeah, so what I want to emphasize is that by using this Levi-Civita regularization, we can, in this setting, suddenly divide or distinguish two different sides. So we can either distinguish, so when drawing. So this here is the collision point, which, oh, that's not the color. So let me see. So this here in the collision point corresponds to this collision Lagrangian. And that's on the starting point of our orbits. And then, so then we can decide. So either we want to look at trajectories which start in this collision point Lagrangian and end in this this Lagrangian. This would then correspond to symmetric consecutive collision orbits which move like this. Or we can look at consecutive collision orbits, and then these would correspond to orbits which move like this here around. So we can distinguish if our orbits are of that shape or are of that shape. So that's the message I want to bring across. Yeah. Okay. Now, some motivation why it might be interesting to know such things. So we are, so let's say we have like here, maybe Jupiter, and here moon of Jupiter, and somewhere around here, and we want to maybe make some observation of this moon and send information back to the Earth, and then maybe travel further to other directions, to maybe another moon here. So now what we know that it always exists are such orbits. So we can fly here, have our first collision, where we can fly very close to the moon and maybe make some nice observations, some nice probing. Then we fly back around. Then we are facing here nice towards the Earth, so we have easy time communicating with Earth. So sending information, maybe getting some new instructions, and then we can loop around, and then maybe here boost to get out of the gravitational influence of this moon, and then have enough energy to travel to a new, to a different kind of moon of Jupiter. So knowing this orientation might be quite useful. So if you maybe are exactly in the other direction, things get way more complicated with communication and stuff like that. So I think it can be an interesting tool to have if you are planning space missions. Yes. So now after all this motivation, let's talk a bit about the tools we use to prove this theorem. And the reason why we were so interested in oh, sorry. Let's see if we can fix this. Okay. So one reason we were interested in all these Lagrangians is because we can then use it very nicely in combination with the Lagrangian Rabinowitz Floer homology. So what's the idea of Rabinowitz Floer homology? So we are given a Hamiltonian system, and now we want to estimate the number of Hamiltonian trajectories which start and end in a given Lagrangian submanifold. So here I want to concentrate only on one Lagrangian because it's a bit simpler to explain, and one can actually show that in our case, there's a Hamiltonian diffeomorphism between those Lagrangians. And if you have these Hamiltonian diffeomorphisms, one can show that it's actually not so different, or we can come from this case with the two Lagrangians very easily back to this one case Lagrangian. Okay, so the idea is now how we want to estimate this number of Hamiltonian trajectories is by using ideas very similar to Morse homology. So we also here define a function, which is of course now more functional. So it depends on paths on our manifold. And here this t is a constant. It's actually not that important now, and to get the broader idea. And here that's the one form, so our omega needs to be exact. And so that's now the form of our function, which is not that important, just so that you know. And so this is a function on a manifold, which is now, of course, an infinite dimensional manifold. It's the path space on our manifold M. And the condition on this path is that they start and end in our Lagrangian L. Of course, times R for the constant here. Yes. Okay, so that's the setup. And so if you know Morse homology, you can more or less think of this as your Morse function very roughly, and that's your usual manifold. Of course, it's a bit more complicated since everything is like infinite dimensional. So the analysis part, of course, it's very much harder, but for now, that's a good analogy. And now the reason why we chose the functional in this way is the following. One can show now that the critical points of this functional satisfy the following important equation. So it's just a solution to the Hamiltonian equation. And that's the main purpose of this functional. So you don't really need to remember the exact definition, but it is built in such a way that solutions to this functional, critical points of this functional correspond to solutions of the Hamiltonian equation. And so what we, of course, now can do, having Morse homology in mind, is, okay, now we related solutions of Hamiltonian equation to critical points of a function. Now we need to define a homology theory, which then gives us an estimate for the number of critical points of this function. And yeah, that's more or less the idea of Rabinowitz Floer homology. So again, very similar to Morse homology. We also define a Z2 vector space, call it like this, by taking the critical points of our functional now as formal basis. And this will then be our, like the part of our chain complex. The boundary operator we then define on it is again defined by counting gradient flow lines between the critical points. Yeah, so that's the definition important is, which is sum over all critical points, again, like in Morse homology, but we have some like finiteness condition because it's a bit, yeah, because of course we have to make sure that we don't have infinite sums. And now we take gradient flow lines with respect to the function. Yes, and then we count these modulo 2 again. So very similar to Morse homology, at least the idea, the analysis part and the well-definedness questions are of course much harder to answer. Yes, and having this differential now allows us to define a homology theory. So the Lagrangian Rabinowitz Floer homology is defined again as usually kernel divided by image. And one important result or immediate consequence of the definition is that the dimension of this homology, of course, gives us an estimate for the number of Hamiltonian solutions, just by definition, since we took as vector space, this vector space where the basis vectors are just all critical points, and then we just performed some quotient operations, which of course only decrease the dimension. Yes, so that's very obvious, but of course, why is it interesting? And that's the powerful property of RFH is that so if we go to the homology theory, then suddenly this homology only depends on the Hamiltonian system we choose up to homotopy. So everything we had, so manifold, symplectic structure, Hamiltonian, or everything also only depends on this up to homotopy. So the idea usually one uses to use Rabinowitz Floer homologies. We have here like our very hard system. For example, our system now, the restricted three-body problem. And then we try to find a homotopic setting, which is of course homotopic, but much easier to handle. And then we compute the Rabinowitz Floer homology there.
And should the homotopy also be Hamiltonian?
Again?
Should the homotopy be also Hamiltonian or not necessarily?
No, it doesn't need to be a Hamiltonian homotopy, just a usual homotopy. Yes, and then we know we can relate here, they're equal with Floer homology. Yes, and that's the idea how you can estimate the number of solutions by calculating this Rabinowitz Floer homology. Now in our case, we have a small problem, and that is that if you go ahead and calculate this Rabinowitz Floer homology, then it turns out to be 0, which is of course not really what we want for our estimates. So we needed a solution, and the solution we came up with is using an equivariant version of the Lagrangian Rabinowitz Floer Homology. Yeah, so the idea of equivariant Rabinowitz Floer Homology is that so we have a symmetry of our Hamiltonian system, and so far the Rabinowitz Floer Homology doesn't really give us the information we want. So maybe by using the known symmetry of our system, maybe we can increase the strength of the resulting homology. And so what we did is a very simple version of an equivariant homology. So G is, we have a group G, which is finite. And the symmetry of our Hamiltonian system. And since the symmetry of our Hamiltonian system, we can, of course, have also the group action on the critical points of our Hamiltonian. So we have it, or a G action on the critical points of our functional, which correspond to solutions of the Hamiltonian equation. And yeah, so on this vector space, the basis vectors are, of course, these solutions to the Hamiltonian equations, and we can then divide out this G action on them. And then here we have a Z2 vector space, which has as basis the equivalence classes of Hamiltonian trajectories. And then to the differential, we also change this. So here we count all gradient flow lines, and here we count only again up to the G action. Yes, so of course that's a very simple, naive way of defining an equivariant version of Rabinowitz Floer, but it turns out that this is actually enough for us to solve the problem with Rabinowitz Floer homology being 0 and not giving us a nice estimate. Yes, and so then you go ahead and define your G-equivariant Rabinowitz Floer homology. Again, kernel divided by image. And one important thing to remark is that the dimension of this is again an estimate for the number of Hamiltonian trajectories, because so here we start with dimension being exactly the number of Hamiltonian trajectories, then we take the quotient, or dimension gets smaller, take again the quotient, dimension gets even more smaller, and yeah, so this is still a lower bound for the number of Hamiltonian trajectories we will find in this system. Yeah, so.
And could you just maybe quickly say what's the G in the example of this 3-body problem?
Yeah, so I will come to this later, but it will be a Z2 action. Yeah.
Thank you.
Yes. So now to calculate this G-equivariant Rabinowitz Floer homology, we actually found a very convenient way to do it, is at least in a special case. So that's the second theorem. So again, G is a finite group and a symmetry of the Hamiltonian system. And we still have our Lagrangian. And the group needs to act free. Then we need to assume that the intersection of the Lagrangian with the energy hypersurface at energy 0 is at least one-dimensional and connected. So in Rabinowitz Floer homology, you always want to consider the energy hypersurface for energy 0. So what you do if you want to consider another energy, you first, so you H, redefine it by H minus just the energy you want to consider. So that this 0 is not very restrictive. Yeah, and further, let the system be displaceable. So if you don't know what displaceable means, you can also think of just RFH equals 0 instead of displaceable. It's actually more general to consider RFH equals to 0. Yes, and now some condition on the Cohen-Litzender index. The Cohen-Litzender index for the non-constant chords of our Hamiltonian system, so only the non-constant chords, fulfill the following lower bound condition. So the absolute value of our Cohen-Litzender index is bigger than a dimension of the Lagrangian intersected with the energy hypersurface. And if we have all these conditions, then the G-equivariant Rabinowitz Floer homology is equal to the Tate homology of this group with Z2 coefficients and with respect to a trivial Z2 module. So we have this equation here. And so we have here our equivariant Rabinowitz Floer homology, and on this side, Tate homology of G, which only depends on G, which is, I think, is quite interesting. And so the idea is that if you want to calculate this part, you can just check the above assumptions for your system or a homotopic system, and then you can just go to the literature and look this Tate homology up, and then therefore you don't really have to calculate this Rabinowitz Floer homology. Yes. Okay. So I don't, yeah. So the next thing I want to talk about is now the proof strategy of our main result at the beginning. So what we want to do at first was we want to interpret these consecutive collision orbits. So, and again, so we have system, these consecutive collision orbits. We interpret them as starting at the collision point and ending in either here, this is, or I have to say like corresponds in the regularized setting to this Lagrangian. Or if you want uninterested in the other side, you can take ending in this other Lagrangian, which then in the regularized setting corresponds to this one and here. Okay. So after we've done this, we, as I mentioned, can use the fact that these Lagrangian subspaces can be mapped onto each other via a Hamiltonian diffeomorphism and show that the dimension of the Rabinowitz Floer homology, or so it's also true if you just take the G-equivariant version, is a lower bound for the number of Hamiltonian trajectories. And therefore we only have to be concerned about the this homology for one Lagrangian. You don't have to invent the whole theory for using two Lagrangians. And then finally we choose our homotopic system. So as manifold we will just stay in C2. As Hamiltonian we use just the absolute value of our vector -1, so that energy hypersurface is just S3. And as our Lagrangian subspace, we take R2. Yeah, so that's our homotopic system we choose and where we did the calculations. So in the system, it's actually not that hard to see that the conditions of our theorem 2 is fulfilled. And then by the invariance, we can of course transfer the result of this Rabinowitz Floer homology to our setting. So we know that this Rabinowitz Floer homology is equal to a Tate homology. Now, what is about this symmetry? So remember we had our L performing this operation. Yes, and so what you see here is that this regularization introduced additional set 2 symmetry by just because if you multiply here Z and W with minus, of course, because of the square this disappears, and because we divide them here, the minus vanishes, and this then gives us a set 2 symmetry. And then we can go ahead and so because we know this Rabinowitz Floer, the normal one, was 0. So we went on to then calculate the Z2 equivariant Rabinowitz Floer homology. And by the previous theorem and the invariance properties of RFH, we get that this is equal to the Tate homology, where maybe quick remark, like this Z2 is supposed to be the multiplicative one, and that's the additive one, but it's not so important now. Yes, and then finally one can just go to literature and look up what the Tate homology in this case is, and you find it's Z2 for every index, and so the dimension here is just infinity, and this then gives us that this dimension of this is infinity, and that's how we got to the conclusion that there are infinitely many of this symmetric consecutive collision orbits. Yes, and I think that's everything I wanted to tell you about this. So thank you for your attention.
Thank you, Kevin, for the very nice talk. Any questions? I actually have a question if no one else does. I mean, so in principle, in very non-generic situations, you could have, rather than not consecutive collisions, you could have multiple collisions on the same trajectory, right? And in principle, those could those generate this infinite dimensional Rabinowitz Floer homology?
Yes, so yes, like I say, in a very so you could of course have these kind of consecutive collisions, right? And then you bounce back and forth, and this then will also increase your count. Yes, but it's a very special situation you probably won't encounter usually in the restricted three-body problem. But yes, if we're very unlucky in certain situations, this infinite consecutive collision orbits just correspond then to infinitely often going around this and count every period as a new orbit. Yes.
Okay, but in principle, you could use that to really boost a lot, I guess. I don't know.
Yeah. So if you have a consecutive collision, yeah, this would probably look like this, and it's still not bad. Of course, you don't have like this infinitely many different one in this situation, but yeah, I think it's still a nice orbit, and you of course always get two, so in other direction also.
Okay, thank you. Any other questions?
Yeah, could you maybe say something about why it is true that the Rabinowitz Floer homology is the same as the Tate of the group?
Yeah, so Tate homology, you have like this long exact sequence of Z2 G modules. And then you have like here some augmentation. So Z2, yes, and that's then what you call a complete resolution. And so what you can do is then if your RFH is 0, you can and you have the symmetry on it, then those become Z2 G modules, and you can take them here, and then so we looked at Tate homology of G with respect to a trivial Z2 module, and so what you then do in Tate is you tensor here with your Z2, which is a trivial Z2 module. Yet then here and since they are trivial Z2 modules, you can use every G action you have on this side. You can pull it here, and then it vanishes because it's that's where it's defined here. And so you have something like going to the quotient of with respect to G here by tensoring this here, and this then if you put in here Rabinowitz Floer, this then down here will give you the Rabinowitz Floer of our equivariant version.
Thank you.
More questions? Okay, then I guess we can thank Kevin again. So thanks a lot. It was a very nice talk. I really enjoyed it.